So today we're just going to introduce you to logs. We're going to talk 5 or so topics so that you can get acquainted. We're going to review some exponent rules that are going to come in handy. We're going to talk about how we can equate the bases so that we can have exponents, we can solve for exponents. Then we're going to learn how to change from a logarithmic to an exponential function. We're going to do exponential to a logarithmic function. And then we're going to talk about how to evaluate the logs. Okay, so reviewing our exponent rules, the very first example I see here is 3 to the negative 1 power. We know if a number or a variable is to a negative 1 power, we need to move it from the numerator of a fraction to the denominator or vice versa. So in this particular case, we know that 3 to the negative 1 is over 1, so currently it's in the numerator, and that will go down into the denominator, making it 1 over 3 to the power of positive 1. All right, so looking at the next example, we have 1 over 9. Remember that 9 does have a power. It's a power of a positive 1, even though we don't write it. It's just understood. If I wanted to take and move that 9 up into the numerator and have it out of the fraction, I could rewrite it as 9 to the negative 1 power. Now, I want you to kind of follow along with this. I want to also redo this. And let's see if we can make it equivalent to something else. What if we took 1 over 9 again? And I bet you could say that the 9 in the denominator, we could rewrite it as 3 squared, because 3 squared equals 9. Now, what if I wanted to take 3 squared and put it in the numerator? I would still repeat the exact same process. That 2 would become a negative to be able to move up, because I needed to go into the numerator. So then you would have 3 to the negative 2 power, which is equivalent to 1 over 9. So our next example has a parentheses, some crazy numbers inside, a fraction. Everything is to the 0 power, and we know anything to the 0 power equals 1. All right, on our next example, I want to remind you before I talk too much about the square root of 3 that everything that we have or know according to like any variables or numbers, when we do variables, we always remember that there is a number of 1 in front. We don't write it, we don't say it, but it's understood to be there. There's also, every variable or number has a power, and it's understood to be a power of 1. Now, just like when we take the square root of something, when you take the square root of, let's say, 9, you need to have 2 numbers underneath. So the square root of 9 is equivalent to the square root of 3 times 3. So we know that we need 2 numbers to make that value come out of the radical. So it's the same kind of idea. When we have the square root of 3, there's a number out front in the little check mark area, like some of you might want to say, that's a 2. Now the 3 doesn't have a power. The power is a 1. Just remember, we can rewrite this as 3 to the 1/2 power. The power of the 1 that's underneath the radical is going to always go in the numerator. The 2 on the outside, meaning square root, will always go in the denominator. All right, let me do another quick example to kind of just make sure you understand. What if I had the 5th root of 3 to the 2nd power, and I wanted to rewrite this? I could easily rewrite this as 3 to the 2/5 power. 2 was the power underneath the radical, and 5 is the denominator, which is the 5 that was out front. And our last little reminder is that when you have a power to power, so you have 2 to the 3rd power, all to the 2nd power, you're going to take the 3 and the 2, multiply them together. So you'll have 2 to the 6th power, which then simplifies to 64 as your total. Here we are with equating the bases. Real quick, I want to remind you that if I have, let's say we have 2 to the 3rd power, just remember that this 2 is considered your base, and this 3 would be your exponent or your power. Some of you might refer to it as a power. So looking at our first example, the idea is to get both of the bases. We have a 7 and we have a 49 as our base, we want both bases to match. And to do that, we're going to kind of look at the larger of the two values that are given in front of you. So we're going to rewrite, we're going to bring down the 7 to the x power and set it equal to a base that matches. So we're going to obviously write 7 again. Is there something that we can use as 7 to the something power that would give us that 49? So we're essentially rewriting 49 as a base of 7 to a certain power. And in this case, we can say, yes, we can put the 2 in our exponent spot, because you know that 7 squared is 49. So at this point, you just get rid of your 7s. We're going to kind of ignore them. We're going to rewrite our exponents that are left. So we have x equals 2. And our answer would be 2, because you plug 2 into for x, and you get 7 squared equals 49. 7 squared equals 49. Here on our next example, you'll notice on the left side we have a whole number to x power, and then on the right side we have a fraction 1/9. There's a couple of different ways that you can approach this. I personally, I want to change the fraction because I don't like to have to work with fractions for very long. I know most of you don't. So what I'm going to do is I'm going to bring down the 3x and leave it like normal. And then I'm going to rewrite our 1/9 into a whole number to a negative power. And let's move that 9 up to the numerator. So that would be 9 to the negative 1 power currently. So, and then don't forget your equals. So now let's look at this again. Oh, wait, now I have a base of 3 and a base of 9. 9 is my larger base. So I can bring down the 3 to the x power. I'm not going to mess with that. Then I can rewrite the 9 as a base of 3. 3 to the second power would give me 9. Now, you cannot forget about this negative 1 up here. So you're going to take this negative 1 and you're going to bring it down. You're going to multiply that 2 to the negative 1 that was already there above. So now you have 3x equals 3 to the 2 times negative 1 is negative 2. So now we have our bases that are the same. So we're going to mark through those, and we're going to just focus on our exponents. And now we have x equals negative 2. For the next two examples, I would like for you to pause the video at this point, work it out, and see if your answers compare to what I have. All right, so I'm back. As I'm taking 16 to the x power, that's the larger of the two bases I'm having to work with, and I need to change. Is there something I can do to the 16 that would give me the matching 4? So yes, I know that I can take 4, and if I square it, I could have a 16. Now, I can't forget about the x. I bring it down and put it out beside the 2. Set equal to 4. We know 4 is to a 1 power. Now we have matching bases. Our 4s I'm going to mark through. And now I'm left with 2x equals 1. I need to solve for x. Divide both sides by 2. And now I have x equals 1/2. In our last example, 4x equals 32, we're going to take a different approach. There's not a common base that's visible to us right now. You can't change the 32 to have a base of 4. It doesn't mathematically work out. So what we're going to do is we're going to change both of these terms to have a matching base. And we're going to use 2 because we know that 2 squared gives us the 4. And we know that 2 to the 5th power gives us the 32. So what we're going to do is we're going to take the x that was originally on the 4, and we're going to bring it down again and make sure that you multiply it to the 2 that you created. And then bring down your equal sign. Now we have matching bases. We're going to get rid of the bases. We don't need them. They're in our way at this point. And we're going to have 2x equals 5. From here, you're going to make sure you solve for x. Divide both sides by 2. And then that way we're going to have x equals 5/2. Leave as a fraction. There you go. All right, so let's talk about what the logarithmic function is. It's the inverse of an exponential function. The way you're going to say it is log base b of y equals x. And essentially, you're answering the question, b to what power equals y? Okay, so here's just a few more tidbits of information to go along with our current unit. if the first word is, the first definition is common log. And what the common log is, if for some reason you do not see a base given, so that you don't have a b value that's given to you, you can assume that that base is 10. So this would be considered a log base 10 of 23. In your calculator, the log button on the front of your calculator, if you just hit log and then type in 23, hit enter, it's already set to be a natural base of 10. So next we have our natural log, and it's written as an ln. It's equivalent to log base e. E is a natural base, and it has a value similar to pi. So we use, how we can solve in relationship to pi. Well, e is a value. It's in your calculator, and all you have to do is do second and like the division symbol, and it'll come in, and you hit enter. It's approximately 2.71828. All right, so the next little piece of information I want to share with you real quick is how we're going to change the base. Our calculators do not come with this function. So for some reason, if you have log base 3 of 5 and you need to change the base so that you can have a common base, you're going to rewrite this. And think of the 3 as in the basement, it's down below. You're going to need to go take log of 5 and divide it by log of 3. Since the 3 was in the base, we're going to put it on the bottom of this fraction. And then you can enter that in the calculator to get your answer. Okay, so on this slide, we're going to talk about inverse operations. We're going to just review real quickly some of the inverse operations that you already do and you don't, without even really thinking about it. It's kind of embedded in your brain. So the first 4 on the left are going to be x plus 4 equals 20. If we wanted x by itself, we would subtract 4 from both sides. And the reason why we're subtracting is because what was happening to x originally? Well, x was being added to 4. And the inverse operation of addition would be subtraction. So that would leave us with x equals 16. So then we would go to the right side, and now we have 4x equals 20. Well, what's happening to the x? Well, it's being multiplied to 4. And the inverse operation of multiplication we know is division. So we're going to divide both sides by 4, giving us x equals 5. And then the bottom left, we are squaring something. So the inverse operation of squaring would be square root. So we would take the square root of both values, and the square root and the 2 would cancel, and then you're left with x equals plus or minus 2. And then our bottom right, you have the square root of x equals 4. To the inverse operation of square root would be to square. So you square both sides, the square and the square root go away, and we're left with x equals 16. So let's take a look at our next example. So log base 3 of x equals 2. In here, you can see that our base is a 3, and that's what we're going to use to get rid of the log base 3. So it's called exponentiating. We're going to exponentiate the left side and the right side. So we're going to take the base, it's a 3, and we're going to write it down and to the left. I'm making it kind of larger on purpose, and what I do to one side, I'm going to do to the other. And when I write it on the right side, I'm going to go just to the left of the 2 and right below it. So the 2 kind of looks like it's in the exponent's position of that 3. So the log base 3 and the 3 are going to cancel each other out. And then I'm left with x on the left side equals 3 to the second power. And we know that x equals 3 squared is 9. And that would be our answer for this particular problem. On the final example, you'll notice we have 4 to the x power equals 16. I need to introduce the word log because it's obviously an exponential form because x is in the exponent's location. So we're going to introduce the word log into both sides of this equation. We are going to still utilize the base again. So looking here on the left side, my 4 is considered my base. So we're going to log base both sides. So I'm going to take a log, repeat my 4 as the base from the exponent. And then what I do to one side, I have to do the other. So we'll put log base 4 on the right side. So now we're going to cancel. The 4 is the base from the exponent with the log base 4 that we put in there. And now all I have left on the left side is x equals, and then we're just going to write it. I'm going to start with the word log base 4 and then bring down that 16. And that would be it. So x equals log base 4 of 16. Now you have it written in a logarithmic function form. Okay, so here's some more examples that we're going to go through one by one. It says that the directions tell us that we want to write as a log. So that means we need to introduce the word log into each one of these examples because currently you do not see it in anything. So the first example, I'm going to look at my base, which is a 4, and that means I need to log base 4 both sides. And then the next thing would be that the log base 4 and the base 4 from the exponential part cancel. Now I'm left with 3 equals log base 4 of 64, which tells me 4 to the third power equals 64. All right, the next example. Again, I'm just introducing the word log into these equations. So I'm going to take a look at my base from my exponential side of the function, and that's a 5. So I'm going to log base 5 both sides, and the log base 5 and the 5 of my base from the exponents goes away. And then I'm writing what's left is negative 2 on the left side equals log base 5 of 1 over 25. And that would be it. On the next example, I have 1/2 to the x power equals y. I'm going to do the exact same thing. My base is 1/2. So I'm going to do log base 1/2 on both sides. So my 1/2 base and my log base 1/2 cancel. That leaves me with x equals log base 1/2 of y. All right, in the fourth and final example. All right, in our last example, our base is 3. And so I'm going to do a log base 3 on both sides. I'm going to cancel out the 3 with the log base 3, that leaving me with 5 equals log base 3 of 243. And there you have it. So next we're going to take our logarithmic functions and turn them into exponential functions. And to do that, we're going to look at the bases of our log functions and use that as a guide. So the first example, you're going to take the 2 from our base and we're going to exponentiate it. So I'm going to write it off down and to the left on both sides. What I do to one side, I do to the other. And remember, at this point, we are going to take the log base 2 and the 2. This will cancel on the left side, leaving us with 1 over 16 equals 2 to the negative 4 power. On our next example, notice, remember I told you we're going to use our base. Well, here, our base isn't written. So we talked about that a little bit ago, that would be a base of 10. So you actually have log base 10 of 10,000 equals 4. I'm going to use this base, however, to help me exponentiate both sides. So we're going to put a 10 down below on the left side and the right side, and that 10 and that log base 10 will cancel, and then I'm left with 10,000 equals 10 to the 4th power. Our third example, you'll notice our base is 1/3, so I'm going to take 1/3 on the left side, 1/3 on the right side, and we're going to exponentiate both sides. So the 1/3 base cancels with the log base, and then we're left with x equals 1/3 to the y power. Our final example has an ln of 1 equals 0. Remember, I'm going to show you two different ways. The first way is I'm going to start with the inverse of an ln, which I told you was an e, and I'm going to write e on both sides. So e and ln cancel, and then that leaves me with 1 equals e to the 0 power, and anything to the 0 power equals 1. Now the other part I'm going to show you, I'm going to rewrite this real quick, and we're going to have ln 1 equals 0. I also mentioned earlier that ln is the same as log base e, and then so ln is replaced with log base e of 1 equals 0. So using what I told you earlier, our base is an e, so I'm going to exponentiate both sides using e. So e on the left, e on the right. So log base e and e cancel, leaving me with 1 equals e to the 0 power, the exact same answer. So here's all your answers for these examples. Hopefully this all makes sense. If not, go back and rewatch it. Let's go over the steps to evaluate a log. The first step says that we need to set it equal to x. So let's go over to the right, and we're going to set this example equal to x. Then the next thing that we're going to do is exponentiate both sides to cancel the log. So we're going to remember this is based on the current base, which is a 3. We're going to take the 3 and put it on the left side and the right side for our base. And then we're going to cancel the log base 3 with our 3. That leaves us with 243 equals 3 to the x power. All right, so next we need to equate the bases. Remember, we're going to take the 243 and we need to have the base that matches the 3 on the other side. So we're going to come down and write the 3 to what power equals 243. And I know that 3 to the 5th power is going to equal 243, and then bring down the right side, so 3 to the x. Here, our bases are now the same, so I'm going to mark through my bases. Kind of ignore those for the time being, and now we have 5 equals x. Here we are with our last set of examples. The first example says that we need to, we have a log base 7 of 49. Remember, our steps tell us that we need to set this equal to x. And after we do that, we're going to exponentiate both sides. So we're going to look at our base of 7 and use that. So this is exponentiate the left side and the right. Remember, we're going to cancel our 7 with our log base 7. And that now leaves us with 49 equals 7 to the x power. Again, we're going to make our bases match. So we have 49. We know we can make a base of 7 to the 2nd power equals 7 to the x. Get rid of our bases. Move those out of our way. And now we have x equals 2 as our answer. All right, the next example. We're setting our next example equal to x. We're going to exponentiate both sides using 7 again. So we're going to cancel log base 7 and 7, leaving us with 1 over 343 equals 7 to the x power. Now on this one, we need to look at the base of the fraction, and let's kind of focus on that 343. So we know that we need to go 1 over 7 to something is going to equal that 343, and I'm going to go ahead and bring down the other side, 7 to the x. So 7 to the 3rd power is going to equal 343. Now we don't want to leave it as a fraction, so we need to make sure that we move this 7 to the 3rd power up to the numerator like we talked earlier about how to do. So that will give us 7 to the negative 3rd power equals 7 to the x. Go ahead and get rid of our bases because they're matching. And our final answer would be x equals negative 3. All right, the next example, again, set an equal to x. This one you can see does not have a base written, so I'm going to write a base of 10 in here just so you can kind of see it. And we still need to exponentiate both sides, so base of 10 on the left, base of 10 on the right. The log base 10 and the 10 cancel. And that leaves me with 1,000 equals 10 to the x power. We want our bases to be the same. So we know that we're going to have 10 to the something power equals 10 to the x. So 10 to the something power equals 1,000. We know if we plug in our calculator, you can do trial and error, but it'd be 10 to the third power would give us the 1,000. Our bases are now the same. So we have x equals 3 as our final answer. All right, our next and final example, I said equal to x. Our base is 2, so we're going to exponentiate using the 2 on both sides. The log base 2 and the 2 cancel, leaving me with the square root of 2 equals 2 to the x power. Now, how can I rewrite this so I have the base of 2 on both sides? Well, we talked about it earlier. I can rewrite the square root of 2 as 2 to the 1/2 power equals, bring down the 2 to the x power. Our bases are the same. Mark through those, and now we're left with x equals 1/2. There you go. It's our final answer.